I have the pleasure of introducing Mike Adler, who's going to speak and present some very beautiful photos of a New Zealand trip that the GJH organized last year. So I know many of you know Mike, but for those of you who don't, Mike graduated from MIT in 1971 with a PhD in solid-state physics. That isn't quite not necessary anymore. So Mike spent his entire career with GE from 1971 until 2000. Little louder, okay, all right. And he has published over 100 papers. He is a fellow with the IEEE Engineering Institute and has been the president, IEE president in 2003. Mike has been pursuing hobbies, although I don't think it's really a hobby. He's pretty active with it in astronomy. He has some telescopes in an observatory and does a lot of very sophisticated work. He also likes photography and traveling with his wife, Virginia. And without further ado, I introduce Mike.
Thanks a lot. As Mike comes up, I've been reminded I should ask everybody to turn these off in recognition of our speaker. That would be appreciated. Thank you.
All right. Well, thank you all for coming to attend this instead of listening to the President's State of the Union address. I can't promise. Anyway. Yeah, so this trip this talk is going to be about this, mainly about the South Island in New Zealand. Virginia and I have been there 4 times, but the most recent trip was a trip that the Geologists of Jackson Hole did almost a year ago, and a number of people in the room who were actually on, about 25 of us were on that trip. It was the 3rd of these type of trips that I helped organize, so I'll tell you a little more about that as we go on. Anyway, we'll talk about this picture a little later in the talk, so it'll come again. But first, just a little background as to New Zealand itself. Where is it? Well, it's down here, opposite Australia, and here's North America. This is the latitude and longitude of Christchurch, which that makes it about 5 hours sun time earlier than us, plus 1 day, because it's on the other side of the date line. But then it's also, probably more notably, particularly if you're flying from here to there, it's 6,000 miles south, so it's a ton south. It's about minus 43 degrees south in the middle of the South Island. We're 43 north, so that's a big jump. Okay, so a little bit about the land area. Here's New Zealand itself, the North and the South Island. It is a part of this large continent, continental fragment, if you want to call it, called Zealandia, which is surrounded, which I have, and this thing is the red dashed lines. And so it's actually a huge area, but New Zealand's about 5% of that. And all of this pink areas, it's all above below sea level. So New Zealand and New Caledonia are the only part of Zealandia that are actually above water. Then the bluer areas are areas where it's a little bit lower. So interesting thing about New Zealand, well, there's a lot of interesting things about it. Well, probably one of the more notable things about it is that this small continent sits, as it points out here in the words, uneasily on 2 continental plates, 2 different continental plates that are moving on the Earth's surface. So that makes it one of the reasons why lots of geological activity occurs on New Zealand. Some of it, not all of it is good in terms of volcanic activity and earthquakes. We'll get to that a little bit more. So the boundary, so here's the Australia plate over here, and here's the Pacific plate here. And we'll talk about the movement a little bit later, but basically the Pacific plate is underneath the North Island. So the North Island is on the Australian plate, but this plate is subducting it. And this is the plate boundary. As you go into the South Island, the boundary is, and this is the Marlborough area, and the boundary is here, and then it passes on to this, what's called the Alpine Fault, which is the major geological feature of New Zealand. And so the South Island is mostly is on the Pacific plate. So you have these two islands on two different plates, and both are moving in totally different ways too. We'll talk about that as well. Yeah, and I already mentioned this. The amazing thing is that this plate movement, you can see it on the graphic here, is 30, almost 40 millimeters a year of movement and almost 50 millimeters a year. That's a fantastic amount of movement on a geological scale. If you do a little math and say how many, over millions of years, this is a ton of movement. And although the movement has really picked up most in the last 20 million years. New Zealand 20 million years ago was below the sea level, or most of it was. A major difference, though, is that on the South Island, the movement is what's called strike-slip, is that there's movement along the fault, and so there's movement left and right and up and down on the South Island. On the North Island, it's the movement, the plate, the Pacific plate is underneath, and so it's subducting. Because of that subduction, there's a lot of heating goes on because of that, and there's a lot of volcanic activity on the North Island, but almost none on the South Island. Okay, moving on. This is a geological map of the rock in the South Island. The talk is going to be almost all about the South Island, so that was the trip that we took, was just on the South Island. The major rock element on the South Island, in fact, there's a lot of it on the North Island too, it's something called Greywacke, which we'll talk some more about, but it's a form of sandstone that consists of quartz, feldspar, and rock clasts that are actually quite hard, and they're good mountain builders. A lot of this rock, and that's this blue area here, a lot of this rock, this Greywacke, is metamorphosed into varying grades of schist, and that's this purple color here. The Greywacke is about 240 million years old, and this is somewhat younger than that. There's limestone on the coast, that's this cream-colored stuff on here, and some in the inland too. And then there's also granite. There's granite, this pink area up here, a lot of this is granite. There's a little bit down here. And the oldest rock on the island is Precambrian or Cambrian gneiss, which is about 500 million years older or older. And then there's a couple of areas that are no longer volcanically active, but it's volcanic rock on these two peninsulas, the Banks Peninsula and the Otago Peninsula are volcanic rock. And then there's some older volcanic rock spread out in a couple of different places. But most of it is Greywacke. Okay, so talk about how did New Zealand come to be where it is? And maybe I'll use this screen for a while and talk to people over here. Okay, so one of the interesting features is that New Zealand is recycled. Most of the rock in New Zealand is recycled. So New Zealand really didn't exist 200 million years ago. And what it is all the runoff from rivers and lakes from this Gondwana supercontinent sent it ran off into the ocean, and it gradually built up over eons, millions and millions of years as these sediments came in, and some of the oldest rock as well. And as I mentioned earlier, the oldest rock is 500 million years for the gneiss, that is, and 360 million years for the granite. Greywacke is about 240 million years old, and the schist, which is metamorphosed versions of the Greywacke, is younger than that. So that's 200 million years ago. This is a snapshot of New Zealand when it was still connected. It had now, by 100 million years ago, it had built up along the coastline, if you will, of Gondwana. And this blue line is where it ultimately fractures. And what causes that fracture? Well, all of these supercontinents, after they've been together for a while, heat builds up underneath them, and that heat, buildup of the heat, causes expansion, and that expansion caused it to break along this line. And because of that, Zealandia, which is the larger continent, was now moved off into the Pacific. So this actual break occurred about 85 million years ago, and the area between Gondwana and what is Zealandia flooded essentially, and this became the Tasman Sea, and New Zealand just moved off into the Pacific. It took about 30 million years for it to reach its current location in the Pacific Ocean. However, around the Oligocene, let's just say 35 million years ago, as it moved off, it descended into the ocean, and there was only just a few little bits of it that were above sea level at that point. But what was going on during that time was that New Zealand, a lot of coal deposits were created, as well as limestone. Limestone was forming on the base, at the sea, below the sea, on the bottom of the ocean. But these millions of years of limestone were present, and this limestone now exists, as I showed you earlier, on the actual islands of New Zealand. We'll talk some more about that. So, but then a big thing happened about 25 million years ago, and the plates got very active. There was a spreading ridge that occurred between Australia and Antarctica, and that became active, and as a result of that, the Pacific plate started moving relative to the Australian plate. And in the north, the Pacific plate, as I mentioned earlier, actually dove underneath, subducted the Australian plate. And on the South Island, the area just broke up, but eventually coalesced into these faults, the Marlborough Fault and this great Alpine Fault, which is almost a perfectly straight line. And so these formed, and then, but they continued to move. So there was a twisting action of motion this way, and this way, and as a result of that, as well as volcanic activity on the North Island, as a result of that, there was a lot of uplift that occurred. And so a huge amount of mountain building began pretty much about 5 million years ago at the edges where the continents are colliding. And on the South Island, it occurs along what's called the Alpine Falls. And the Alpine Falls is where the Southern Alps currently exist. So if you want to look at a little bit of history, this is Zealandia over the last 80 million years. Here it is 80 million years ago, still connected to Gondwana, and then it gradually breaks apart and reaches where it is right now. But remember that this is mostly a submerged continental fragment. And the islands of New Zealand are tiny little pieces of that. So this is what we have at the moment, and things are still going on. So what that uprise that created the Southern Alps and brought the two islands above sea level is continuing. And there are areas that the color here indicates how much uplift is going on as we speak. Most of that uplift is occurring on the Southern Alps, and that uplift is over 5 millimeters. In fact, it's actually more like 10 to 15 or 20 millimeters. If you think about it, again, fantastic amount of uplift from a geological standpoint. And there's a few areas, the green areas are subsiding, but most of it is either uplifting slowly or very quickly along the Southern Alps. So what else is going on? Well, right on these faults, there's lots of faults in New Zealand, and there's a major fault system on the North Island, which if you got an earthquake of the size that occurred in Christchurch on the North Island, particularly in the bigger town, it would be a major disaster, something that is just a fact of life that people have to deal with when living there. On the South Island, you have this major fault called the Alpine Fault. We'll get back to that. And then you have these many different faults in the Marlborough area here. Then down here, this is zooming in on the Christchurch area. This is the Banks Peninsula. And these red areas are areas of volcanic activity. And you probably all know that that there was an earthquake there in 2011, in 2011. I'll talk about that in a second. But here's the Alpine Fault sketched out. And it's interesting that up until 1941, people didn't even know it existed because the area was very rugged where it exists. And it was only through satellite pictures. If you look carefully here, you'll see it's a very clear line that runs down. That's the Alpine Fault. And that is the major geological feature of certainly the South Island. And, you know, a little bit more context. Here's New Zealand right down here in Australia. This is what's called the Ring of Fire. And it's an area where there's a tremendous amount of earthquakes and volcanic activity. And all these black areas, every dot represents an earthquake since 1964 to 1999. Tremendous amount of earthquake activity in this area. And then this picture is an unfortunate picture of Christchurch after the 2011 earthquake. And Christchurch is still recovering from this. It produced an earthquake. It was 6.2 magnitude and produced a movement, 2.2 gravities, G's worth of ground movement, which caused a major amount of damage. And it's interesting that this is not on a major fault. This graph shows, go back over here, this graph shows the probability, the 10% probability of earthquakes in New Zealand in the next 50 years. And the, let's see, is this thing still working? No, it just died on me. Oh, batteries. John, I guess, let's see, will it still advance me? Okay, it will advance, but so I guess I'll do the other pointer. There's the button. Okay. So this is the 10% probability that there will be a earthquake of varying magnitudes in New Zealand. And the colors indicate the severity, that is how many G's of movement there will be on the ground. And you can see the pink area, or the pink and orange and red approach 1 G, although as I said just a second ago, Christchurch had 2.2 G earthquake, and that was just down here, which shows a very low probability of any further activity. The biggest probability is along the Alpine Fault, where most of the strain exists between the collision between the Pacific Plate and the Australian Plate. Okay, so moving more towards the trip itself, we had 3 guides, all from the University of Otago. I'll tell you a little bit more about how all that happened in a bit. But we had Dusham Yugan, who is a PhD from there, studied in that department. Then we had Andrew Gorman. Dushan stayed with us in the entire trip. He was with us for all 16 days. Andrew Gorman actually is a Canadian, and he was with us for the middle part of the trip. And then Michael Palin, who was actually American, and he was with us towards the end of the trip. So this was the itinerary. We started in Christchurch, and for those of us who were there, this was a very unfortunate day that we arrived. It was the day of which this massacre occurred in the mosques in Christchurch. That occurred on the day as we were arriving. It was a terrible disaster. We were in shutdown mode in our hotels, but it actually didn't affect our trip. In spite of the tragedy of it all, we were able to do the trip pretty much as planned. We spent the first day on the Banks Peninsula, then went up and spent to day 2 towards the north coast. We spent several days up here, then went over to the west coast, spent several days here, then went down towards Westland National Park, where we visited the Alpine Fault. We went down and spent 2 days in this area of
Lake Tianau, did a boat trip, then came along. Actually, we did do a little trip down here to this area, and then we ended up back at Christchurch. So this is an aerial picture of the Banks Peninsula with the Southern Alps in the distance here. This area was volcanically active 10 million years ago. One volcano was right here, and there was another one up here, and they're currently harbors. This is the Akarora Harbor, and this is the Littleton Harbor. There is no current volcanic activity on the South Island. This is a view of overlooking the Akarora Bay. Actually, I'm going to talk about a peninsula that you'll see here in a second. That peninsula, O&I Peninsula, is right here, and I'll mention it. So this is just a view coming down into the bay. And then we explored this very interesting rock, which is on this O&I Peninsula, which is basically volcanic rock. It's basalt, but it was been metamorphosed and additional elements crept in to give it all this fantastic color. And it's called migmatite. And you have, and so not only is it colored, but it's twisted and contorted, so a lot of movement has occurred. And so here's Dushem explaining all of that to us, and you can see just how beautiful all this rock is. There's a ski pole to give you an idea of the scale. And some of us took a little bit of a hike up onto the peninsula after exploring the area that we were showing was all down here. Then after leaving Christchurch, we went up and we made a stop at Ward Beach and Chancet Rocks. And so this is a picture of incredible blow Chancet Rocks. It turned out it wasn't like this when we were there the first time. Virginia and I stopped by on the way up towards the end of our trip, which lasted a little longer than the geology trip, and it was just blowing a stink. Interesting, we saw a nice little collection of seals here. All of this rock is a beautifully white limestone, and with some additional elements added into it to give it this color. In fact, one of the interesting features of that particular location is that there is this band between two of the limestone here and limestone here. Then there's this band here. This has been identified to have occurred 65 million years ago when an asteroid impacted, a huge asteroid, and ended the dinosaur era. And this is the KT transition. So that you can actually see that transition at the right point of tide in that at Chancet Rocks. And this is just some more pictures of some of the limestone here, and this is chert. That's a mixture of silica from various other creatures mixed in with the limestone, creating this much harder rock. Okay, so that's Ward Beach. We then made our way up to Nelson and spent part of a day there. One of the interesting features of the Alpine Fault and the activity around it is that over the last 20 million years, all this movement along the Alpine Fault separated areas of the same type of rock. So this area and this area were once together, and over that period of time 450 kilometers of displacement occurred along this. As I remember, I told you that the motion here is not just it's not left and right. A lot of it, in fact the bulk of the motion, is actually along the fault. So that caused 450 kilometers of displacement. So you have the similar rock, this reddish color rock, both down here in the south and in the north, are the same rock. And what it is, it's mantle rock, and it's called dunite, which is a rock that contains olivine and other high ultramafic, meaning high iron and manganese, low silicon rock. And so pretty remarkable. And so the first day when we were in Nelson, we investigated an area here. Now, as it turns out, that our guide, Dusham Yugen, did his PhD thesis on this stuff. And they're called, these are more generally called ophelites, and they're about 270 million years old. And how do they get here? Because they're on the mantle, which is normally buried underneath quite far down. Well, it's all of this plate movement and the collision of the two plates that brought this mantle rock up to the surface. And we're not seeing, we're all here along the riverbed, we're not actually, the top of the mountain is where the mantle rock actually is. Here we're seeing fragments of it, and this just happens to be one piece. So it wasn't all geology, and we did stop and look at some other highlights of places. This actually was our first group picture. Here we all are, and there's our guide. And this is at a place called the Resurgence, which is up in the Nelson area. And it's an area where the Maori would go for cleaning and healing. And it's a very beautiful spot, as you'll see in this next picture. So it's it's almost a religious location as far as the Maori are concerned. Okay, then we went up to the very tippy tip of the South Island, which is Cape Farewell, and we did a group hike on the Waroriki Beach. And here's Carol Ferris changing her shoes and what have you, and there's a group of us out here commiserating. This is just some of the scenery on that beach. And there was a fair amount of active bird life. And this is a picture of the beach itself, Waroriki Beach, and that we walked along. This is actually Cape Farewell itself. This was taken in our previous trip, 2006, but this is all sandstone. 130 million years or so. Then we also, this is a cave that we visited, and there's a sleeping seal underneath there. That was actually taken on this trip. Okay, so there we were up there. There's Cape Farewell. So now we're going to go over to here, but there's no road in New Zealand along this part of the coast. You can walk it. There are walking tracks. New Zealand, particularly the South Island, is filled with what they call the Great Walks, and there's one that takes you along here. But what we had to do was go back down to Nelson, come along here, and then go over to Westport, and then we were able to go up by road to here. So along the way, we passed through an area called Buller Gorge, which is a 60 million year old limestone over this very old granite, and it's called Karamia granite. And here's some of the limestone right along the river level. And here you can see this very pink granite rock. And here's a close-up picture of the granite, which is very colorful, large crystals you can see because of the coin here. And it's a mix of feldspar, biotite, and certainly quartz. So at this point, we broke up into two groups. We had a bus, I didn't mention this, we had a 40-passenger bus for the 25 of us, plus a van. Unfortunately, we wanted to go up to this area along the North Shore, but the big bus couldn't make it. So there was only a group of about 9 of us that were able to get up here to see this area. This area is all limestone, and this is a huge block of limestone that got pushed over you don't really notice it. This is a picture I took at the sea level, but that's from the air. This is what it looks like. And this is where the road ends on the west coast. But this limestone is about 25 million years old. And it was the limestone that I mentioned that was formed when New Zealand hadn't risen up yet out of the sea 25 million years ago, and it was the limestone that formed under the ocean. So there's limestone offshore here as well as along the shoreline in this location. Plus, as you go in a bit, there's granite underneath the limestone as well. So this is one of the main features of this area, and they're called the Operaro River Arches. And so here's the arch, and it's quite huge. This arch is the biggest arch in the southern hemisphere. It's 220 meters long and 43 meters high and 79 meters wide. It's quite big. It was, as I mentioned, formed about 30 million years ago. How did the arch form? Well, New Zealand, and particularly on the west coast, gets a ton of rain. 6 meters of rain a year in this area, meters. And the acid in the rainwater gradually erodes the limestone, and in some cases like this, an arch results. This is another arch that's much smaller, but is very pretty because of its location. And it's a nice reflection. And this is the group that did that part of the trip. And cave underneath. You can get to this arch by a cave system that again has been etched away by the flowing waters over the eons. And I think this is Brent over here, yes. Brent Schaefer. And this is another view of the cave system. This is all granite here, so the limestone is over that, and this is granite. And then we have a bush robin sitting on my hiking pole. Okay, so that was one-day adventure. The group reconvened, and we visited a place called Pupu Springs, which again has a Maori tradition to it. Very beautiful, clear water, and that was just a little side trip. But an unfortunate thing happened after we left this, and this is what happened. And those who are on the trip will remember this very well. The bus driver tried to cut this turn a little too tight, and he grounded the back of the bus, and it got hung up. And this could have been a bad story, maybe wrecking the trip. But Mary here went out and flagged down this vehicle off the highway. Yeah, and they came to our rescue. And here you can see them trying to pull us backwards up, and it didn't work. But they eventually gave that up, and they went around and they pulled it from the front, and that busted it out. And the truck, and amazingly, the bus was not damaged. But that whole thing could have resulted in days of delay on the trip. Fortunately, it was just hours. It turned out to be a little bit of an adventure, is all. But it was only because of Mary's action here that we were able to recover this so quickly. So, so after that, we then did we were doing the drive, and we're on Cape Foul Wind. And Cape Foul Wind was named by Captain Cook in 1770, who visited this area, and he basically named it because of the persistent rain and gales that this place had. And the name has stuck. So it's still called Cape Foul Wind. However, there are days, not so much on this day, but this...
Go back and point out the person in that picture.
Oh yeah, there's a person right there. Yeah, yeah. Yeah, this picture was taken in 2016, I think, when Virginia and I were up in this area. But here's Cape Foul Wind on this trip at towards the end of the day. This is actually the same day we came back down from the Upper Rural Arches, and I took this picture at the end of the day with the nice lighting like this. One of the other features at Cape Foul Wind is a seal colony, and unfortunately the tide wasn't quite right the day we were there this year, but in 2016 it was. What was happening is big waves had formed, and they would break over the top of this, bringing lots of fish into this little bowl, and then the seals would go on to a feeding frenzy, going after the fish, and it was quite entertaining to watch. Okay, so that was all up in the Westport area, and then so at this point we started heading south along the west coast and to Punanaki, Pancake Rocks, and we'll talk about that now. So this is an aerial view showing this limestone sloping to the south along the coast, and the Pancake Rocks are located right here. And the Pancake Rocks were formed, again, the limestone layers built up over the eons, but then they got eroded, they got uplifted and then eroded in an interesting fashion to produce things like this. And so you can see it's layered rock, it's layered limestone with somewhat softer mud layers in between, and over time the mud layers get eroded by water and wind, and creating the pancakes that gives this place its name. And this is another view looking south along the coast. We didn't quite have, truth in advertising is we didn't have quite this much sunlight the last time. This goes back. But one of the other features of this area is this area that has gotten etched, eroded out, and forming this a little closed area in here. But the sea, it's not totally closed. The sea can come underneath. There's a hole here, and there's some caves here. And when the tide is right, the water sloshing into the cave causes the air to compress, and it sounds like a big foghorn. The caves are underneath here. And again, it was only 2016 when we were here that we heard that. But anyway, it's quite an impressive place. It's a lot of very natural beauty here. Okay, so and this is a view looking along the coast. You can see the coastal road. There's only one road along this coast, and I'll get to that, the significance of that in a bit. But now we're heading further south, and we pass by Greymouth, which is the largest town on this west coast, and you can see these bands of limestone that you can see there. I walked up to it when I was here the last time and took these close-up pictures. Okay, so we now mark a change in the trip in the sense that Dushan was with us. Now we have Andrew Gorman joining us at this point, because he's going to take us down into the area to investigate the Alpine Fault and into the Westland National Park. So this is a little trip that all of us did. We visited a couple of sites first, and we all boarded this bus, Alpine Fault Tours, Exposed, and we went and to the fault. You have to do it on a tour because you cross private land. Well, here's a picture of me. Now, I'm trying to show how this whole trip started. Brent, after I had organized the Scotland trip and a trip in Iceland, and Brent was, when we were in Iceland, he says, I would love to go to New Zealand. And he said, well, okay, so what do we do about finding guides? And he says, well, if you can find the guides, that is me, he's telling me, and set the itinerary, I'll do the work about dealing with hotels and a lot of the logistics. So we came up with that deal, but the question is, where am I going to get the guides? So here's a name right here. It says, if you want more information, call Dr. Virginia Toy, the University of Otago, and there's even a phone number. So I did this, and amazingly, I expected her to sort of say, forget it, but she didn't. And she said she would do it, but she couldn't do 16 days, so she said she'd find 2 more guides, and she did. And so amazingly, we had the guides. I didn't think this was going to happen, but I had done the same thing, by the way, for Iceland. I had a guidebook, and I called again, talking about going to Iceland, but needed a guide. So I called the author of the guidebook, and he amazingly, a long story short, he eventually was our guide on that trip. So I did 2 cold calls, and both times I've been able to find guides that have accompanied us on these trips, and they're great people, by the way. Okay, so this site is actually an observatory, and there are instruments that are drilled down into the sediment at the location of this juncture between the Australian and the Pacific plates. And so we're here, and this is a geological map of this area. Here's the fault. This is the Pacific side, and this is the Australian side. And here's Gaunt Creek that runs through. And so these are these two sites. So that's exactly where we are. And lo and behold, here's the fault right there. And this greenish rock is called cataclysite, which is highly stressed rock that's stressed because of the motion occurring between these plates colliding with each other. This down here, and I'll show you in this next picture, this down here is the Australian plate, Pacific plate, and the cataclysite here, and the fault runs right through here. So here's Virginia, actually going back to our 2016 trip, but the fault runs 600 kilometers up the entire west coast of the South Island. Earthquakes occur here, major earthquakes occur here about every 350 years. The last one was, 4 of them occurred in the last 800, but on the average is 350. The last one occurred in 1717. You do your math, you say they're ready for another one now. But along this fault, there's a tremendous amount of movement. In the last 12 million years, the Alps have been lifted by 20 kilometers in 12 million years. And they're currently rising 10 to 20 millimeters a year. And the only reason that these mountains aren't like Mount Everest is that they are eroding at about the same rate they're rising, at least at the moment. But this area is extremely geological active, and I'll show you a picture of how I figure that out in a minute. But here's just some pictures of the rock. This is this boundary between the cataclysite and the Australian. This is also really a gravel almost. It's been grinding up, but there are a few fragments. And so here's a fragment of the Pacific plate, which is either a mix of the Greywacke and schist, and on the Australian plate, it's granite or gneiss. But sort of the same story, not granite or the metamorphosed granite into gneiss. And so you can see fragments of both types of rocks right in this same area. So here we are, a group putting their hands on the line between the two plates. But we did more than that. The couples lined up, and we'd have one couple on one plate, one couple on the other plate, sort of separate, hands across a continent. They're not really continents, but we can call them continents, plates. And so here's two couples, and Bob didn't join Kathy here for some reason. So anyway, Marilyn is pinch hitting for Bob on this point, but there we are. And this last one is us, Virginia and I, but I'm showing this picture mainly because I want to show you what's happened here. This was a picture that was taken in 2016 at the same spot. And if you look up here, and this is what it looks like in 2019, you'll notice there's a few differences. You can tell it's the same spot because you see this gully here. Okay, that's the same gully here. Notice this little spike sticking up. There it is. But notice this thing isn't there. And none of this rock looks exactly the same by any means. Certainly all this rock is just totally different. So there's lots of activity occurring on this spot. This doesn't stay looking, it's not your normal spot where you come back a few years later and it looks pretty much the same. This looks totally different. Well, it's very interesting. Lots of activity. Okay, and this is the group picture that was in the publicity, so here we all are. The picture was taken by one of the guides. We had a separate guide to take us to this spot, but there's the fault in the background. Okay, so here's the next morning. One of the interesting things here in this area, we were staying at this point in a town and in the park, and we were one of the things to do is to go up early in the morning and to a place called Lake Matheson. And so here's Virginia and And we're here, so this is an interesting story. This is a black and white picture I took. This is Mount Tasman, and that's Mount Cook reflecting. And I discovered something when I was processing these pictures, that if you take a picture in black and white, there's a little bit of haze, and if you take the blue wavelength, you can do that in Photoshop out of the black and white picture, and then reimpose the color on top of it, you get a much sharper color picture. And it's actually sharper than it was visually when we were there, because I took some of the haze out of it by just taking some of the blue, because the blue light is what gets scattered the most. So anyway, so this we were very lucky. It was clear, and there was no wind, at least this early in the morning, and so we got this very nice reflection of the two highest peaks in New Zealand, Mount Tasman and Mount Cook. Mount Cook is 12,200 feet high. And interesting, this is a picture I took in 2006 at the same spot. You'll notice there's a lot more snow. And this is about the same time of year, too. There was a lot more snow in the mountain then. And this is a picture of Mount Tasman down the road a little bit. And later that same day, we went up to, we were staying in the town of Franz Josef Glacier, and we went up and hiked up towards the actual glacier itself. And here's Mary and the Poulthers. These pictures were not taken on this trip. In 2006, our daughter, we happened to have a beautiful day. Our daughter just got a pay raise, and so she treated us to a helicopter ride. And so these are looking at Mount Tasman and Mount Cook. Well, that's Mount Tasman there, and Mount Cook here. And there's a difference in the heights. This is some of the glacier here, and this is just a picture of a waterfall from looking straight down. I should mention that Mike Menelacino, who is here, climbed Mount Cook twice. So he's. This is some more pictures I had taken in 2006 on the other side, on the Mount Cook National Park side. We were on the westland side, the Pacific side. This is on these, but you can see the rock here, and I'm pointing this out because I want to show you this rock. Much of the, I mentioned the rock is largely this Greywacke rock, and we'll talk a bit more about it. This is on a mountain called Mount Sefton, and it's layers of Greywacke with intertwined with a darker rock called argillite, which is black. And when this was all deposited at one point at sea level, it was all horizontal. But look at it now. It's almost standing straight up, and it's because of the plate collision that has caused that. And the plate collision is what's uplifted and created these mountains. And so in one of the guidebooks of geology, they call Greywacke the national rock. And so what is it? Well, the Greywacke, there's a German version of this word. It's not quite like that, but it means gray rock in German. And it's basically sandstone, but it has some unique properties. It has quartz, feldspar, and a class of other rocks that are cemented together in a muddy matrix. It's actually quite hard, and it's a good mountain building rock because it does do a reasonable job of resisting erosion. And this is a picture of the actual Greywacke here, and these are various grades of metamorphosed Greywacke, working its way from sort of semi-schist to high-grade schist. Schist is not is a medium-grade metamorphic rock, and these are the thin sections of the rock. This white stuff is the quartz, and the darker stuff is feldspar, and then there's other bits of stuff mixed in with that. And then you see the change as you get to the higher grade schist. It takes 300 degrees and pressures that you have to get down to about 10 kilometers below the surface to get enough temperature and pressure to metamorphose the rock. And here's some of it. I mean, this is with central Otago schist, and you can see all the layers. When the rock becomes metamorphosed, the elements tend to segregate and create these bands, which are called schistosity. And during the recrystallization phase, you get these bands. Okay, how are we doing on time? We've got to move along. The Tasman Glacier. So this is a picture from the air of the Tasman Glacier. It's all covered with junk here, so it's dark. But over the eons, it has come and gone, but is now going. And this lake that created at the base of the glacier came in the mid-80s, and all the glaciers in this area are receding. This is a picture I took just this year of the Tasman Glacier on this area. The lake is behind me here. And this is a picture looking the other way of the end of the Tasman Glacier. So we did visit one more site in the Franz Josef area where the Alpine Fault was. And here's the Franz Josef village, here's the glacier, and we're over here, right there. And this is the Pacific and Australian plates here, and we're right here. And you can see some of this schist, heavily contorted schist rock here. And this is the cataclasite that forms right at the junction between the two plates. Not as clear, it's not so obvious that where the fault is, but it is here. And here's a river of this cataclasite right at the boundary. There's Andrew, our guide. Okay, so there's been some interesting research done recently, and here's a picture of the Alpine Fault from the air, and you can see it very clearly. It was originally thought to be pretty much vertical, that is, these two plates colliding and then pushing up against each other. But they now realize it is not that way at all. The Australian plate actually is underneath a large portion of the Pacific plate as you go further east. In fact, maybe as much as 100 miles east. And so the junction between the two plates is not just here and going straight down. It exists going east quite a ways. And so when you get potentially an earthquake, and this kind of shows a sketch of it, although I think this really should be much flatter than in the sketch, but it shows what's happening with the Pacific plate colliding with the Australian plate, causing this is a reverse fault, causing the uplift. But in addition, as I mentioned earlier, there's motion in and out of the page, up and down. That's most of the motion is along the fault, not perpendicular to the fault. But when an earthquake occurs, it won't necessarily just occur here. It could occur as much as 50, 60, 70 miles away and may never even break the surface because the contact is below the surface. So it is a piece of relatively new information. The motion along the fault is about 40 millimeters a year along the fault and about 6 to 10 perpendicular with this uplift that I've mentioned a couple of times. So that pretty much that ends the discussion in the Alpine Fault area, and now we're heading to Wanaka, which is here. We take the road to here. Now I should mention something at this. This is a good point to mention a little detail. When we left Franz Josef, the weather was beginning to go bad. It started to rain, and by the time we got to Wanaka, it was raining really hard. It rained real hard on the way. We found out when we got to Wanaka that it rained a half a meter of rain that day. A half a meter of rain. And as a result of that, the bridge that we had crossed many times got washed away. Gone. You'll notice there's only one road along this coast. Not only did that bridge go out at Franz Josef, but the whole road was closed because many different places along it avalanched and slid and closed the road. So we just got past that point before that happened. And the same thing happened in Iceland, where we got the bridge across the southern part of Iceland went out while we were having just passed it a day before. So two times in a row we dodged a bullet. But anyway, so here we are in Wanaka. A bunch of us were sick. We went to a clinic there to get some medicine, and ultimately no one died. Fortunately, we all survived. Okay, so at that point, we didn't really spend any time in Wanaka, and we went down to Tianau. But you notice there's no way to get across here because these are where the Southern Alps are. So you have to go all the way down here and over. And we went to Tianau. And then the goal here was to do a sightseeing trip, plus see some geology along the Fjordland area. And so it's an interesting trip because you have to take a boat, 2 boat rides and a bus ride, and 2 bus rides. So you take a bus to the one end of this lake called Lake Manapuri, and you get on a boat, and you cross Lake Manapuri. And then you get on a bus and you go over this height of land called Wilmot Pass. And this is a view of Doubtful Sound in the distance. And then you drop down to Doubtful Sound, you get on a boat, and you have your boat tour, and then you do it all in reverse. All this infrastructure was built because of a power plant that takes water from Lake Manapuri and dumps it into Doubtful Sound. And there's a power plant that generates hydroelectric power for a limestone plant. So here we are, a group of us on the boat, and amazingly enough, we had a good day because this is an area 4 times. The first 2 times we were here, all you saw were waterfalls. You couldn't see the top of anything, but we were able to. And this is some of the very oldest rock, a picture of this 500 million year old gneiss. And this is a beautiful area. So these are just some pictures on Doubtful Sound. And we had not perfectly blue skies, but actually the clouds made it quite interesting. And so. This is a picture I took in 2016. 2016, we did a overnight tour on Doubtful Sound on a boat that kept us. We slept overnight on the boat. So at that point, we finished our tour of Doubtful Sound, and we were going along the south coast, and we made a stop at a place called Curio Bay, then proceeded up along the east coast. And so Curio Bay is a place that is was once a forest and is now petrified rock. And so there are trees that became silicified very quickly, very soon after flooding occurred, probably 330 million years ago, and they are there still. They've become uncovered, and the mud's gone, and you see the petrified rock. We then went to Dunedin, and this is a magnificent structure. This is the train station in Dunedin. And then we visited the university there. This is the Otago University, same architecture. Here we are at the geology department with Dusham, and we went and explored this area for a day. We went out and had lunch at a place called Tunnel Rock along the coast. And some of us went inland. Actually, this is a picture from previous years. This is the other area on the coast that was volcanic 10 million years ago. So these are all basaltic columns that that formed here. These are called the organ pipes, interestingly enough. Then some of us went out to the peninsula and some nice views, and checking out some more columns and this natural bridge that was formed from the basalt. We also visited a albatross colony, and here's a mature one, but here's a baby that was probably 3 months old then. Would have stayed there until August last year from January, then flies away for 5 years, never coming back to land for 5 years, then comes back to the same place 5 years later. Okay, so towards the end of our trip, here we are. Here's Mary Gridley pushing a big boulder, and Brent. Meraki boulders are called, and here's Mike Palin talking about this. So these boulders were once formed, then buried, and then they've become the mud around them has dissolved, and they're now visible, and it's quite interesting. They were originally mud balls that got infused with silica, actually calcite, and as much as 20%. And in some cases, the calcite has replaced the mud, forming these interesting borders between sections of these boulders. The boulders were pretty much formed about 60 million years ago at the near the surface of the seafloor, and the larger ones took as much as 4 million years to grow into their current size. Then we visited the town of Oamaru, and there's an old section of the town. It's not old by European standards, but over 100 years old. And we had lunch at this beautiful park. The last thing we did was we went for a hike to see this pillow lava, and this is it. And this was an interesting discussion that occurred, because our guide said this is the most impressive pillow lava in the world, and we had some disagreement on that topic, but it is impressive. And what this is lava that forms underneath the sea, and it cools very quickly, forming a outer layer that is solid and with liquid still inside. What happens is then they can crack, and then the liquid spews out, forming another pillow, and you can get these interconnected layers to form this big ball like this, where these individual areas separate. And this is a picture of the outer area of one of them, and it's glassy, so the glassy area forms more quickly, and so it forms glass, whereas inside it might be crystalline or polycrystalline. So that was pretty much the end of the geology part of the trip. Here's a picture of the three guides together. We were up here at Oamaru with that last picture. Virginia and I stayed around, and the rest of the folks went back to Christchurch. And the rest of the pictures are just a few that I took while we were together. This is an area of limestone that's in that Oamaru area that's been heavily etched, and we have some of the local denizens up here with us. This area is glacially created. The lakes were created during the last glacial age. Here's Lake Wanaka, and the next lake next to it. And this is a view of that area from overlooking Queenstown, which is sort of it's on one of the lakes. You can just barely see it here. And that's sort of the capital of this part of southern New Zealand. This is one of the lakes. It's called Lake Haiwea. This is Lake Wanaka. I took this in black and white from top of a small mountain called Mount Iron that we did. This is Lake Wanaka the next day that Virginia and I walked up. Then she and I went up and went into the Mount Cook area, which is right here. And you'll see some pictures. So here's a black and white picture of Mount Cook. What's interesting about being on the east side of the mountain range versus the west side is you see the full exposure. So, you know, I think maybe we're at 500 feet here. This mountain is 12,200 feet, 300 feet. So this is an incredible amount of vertical relief that you don't see in many places in the world, which you have this much vertical relief. This is the colorized version of that picture. Actually, I like the black and white one better. This picture was partially taken in the morning because the mountain peak was visible in the morning, but this was all in clouds. In the afternoon, the mountain peak was in the clouds, and this was open. So I combined the two pictures taken from the same spot and made a single picture. So I cheated. So here are some pictures that were just taken in the park also at Mount Sefton from the river level. This is Mount Sefton, a hike that we did some years before in 2006, and that's Mount Cook in the background. We've done some of the great walks over the years. One of them is called the Routeburn Track, and this is a picture of one of the pictures along the Routeburn Track called Lake Mackenzie. The picture taken along the Routeburn Track in 2006. We had some snowfall that year in the mountains. And then the Routeburn Valley on the end of the Routeburn Track. And the other big walk, which is actually the more famous of the two, is called the Milford Track. We did that also in 2006. And this is the end of the Milford Track. It's at Milford Sound. The Milford Track runs from Lake Tianau to the Milford Sound with a boat trip on each end, and you walk in between the two. And these are the last few pictures of the talk. Emily, our daughter, spends several months a year in New Zealand, and she had given us some places to go, and one of them was called Mount Sunday, and that's what this mountain is here. It's in a big valley. Some of you who have seen The Lord of the Rings may recognize this. This is Eldoras. That was in the movie, one of the major sets, and I think it was in the second. And you look at all of the structure that's here. Look at it there. That's what it looks like now. That's what it looked like then. It's all gone. But this is the site of one of the sites of the Lord of the Rings movie. And this is the view from the summit of Mount Sunday today. So that's it.
Questions, Mike?
Yep.
I want to go back to those earliest slides where you're showing the Australian plate and the Pacific plate close together. And a couple of questions on that, on those slides. One, why do the two plates stick together? Is it subduction? And two, how did they move south? What kind of force moved them south when most of the movement is east and west?
Okay, so here's here. Let's use this one.
Yeah, that one.
Okay.
So most of the movement is east and west, but they actually end up pretty far south of Australia. And they go together as though they were glued together.
Well, they aren't glued together. They're very much not glued together, and it's the motion between the two that's created the islands as well as the mountains. See, so the Pacific, you can see the Pacific plate motion. Well, here it's pretty much east-west, but here it's northeast-southwest, and it's sliding along the Australian plate, but pushing against it.
Split apart, Mike.
What's that?
They split apart.
Well, why didn't they split apart? Well, because plates, that's a bigger question, but plates in general come together and they go apart. And you know, when they come together, they heat up, as I mentioned. That's what caused the chunk, which is Zealandia, to split off, because the Gondwana heated up underneath, and that additional heat caused it to break apart. But then some additional motion, which I mentioned it just briefly. There was a rift that was forming between Australia and Antarctica, and because of that widening there, it caused these plates, the Pacific plate, to start going west.
But they end up fairly far south of Australia.
Well, no, Australia is pretty much right.
Australia moved north.
Here's Australia. Yeah. Well, you're asking a bigger question, which maybe John can now offer some. But the motion of these plates is complicated. It's not simple. Yeah. Yeah. Let's see. Yeah. Well, there's current Australia right there. Other questions? Yeah, John.
How deep is the ocean over Zealandia? Is it close to the surface?
It's pretty shallow. In fact, let's see. There's some scale here. That the greenish area here is here's sea level. So the blue is about 2,000 meters down. So I guess this area is about, which is considered still part of, well, this area here is fairly shallow. It'd be about, well, a couple of thousand meters. And this area here is only, the pinkish area, maybe less than 1,000 meters.
Is it that Greywacke too?
Yeah, a lot of it is. A lot of it is at the sea floor. Yeah. That's. More questions? Yeah. Fortunately, my battery is living on the advancement tool here, and I was able to keep it going.
All right. Is there
if there are any more questions,
Hi.
a couple of